calculus. All right, 4.4 is the fundamental theorem of calculus, and it's going to be putting together a couple of different things we've seen in this chapter so far that didn't necessarily seem super related. And what they're going to do is we're going to talk about what happens when we're trying to find the exact area under the curve from A to B. So the fundamental theorem of calculus says the following: if f is continuous on AB and capital F is any antiderivative of f, then the antiderivative from A to B of f of x dx is the antiderivative of f, right, capital F of B minus capital F of A. And this really is putting together what we've been talking about in terms of area, in terms of notation, and in terms of antiderivatives from the very first section, all into the same set of material. Now, the way in which we do this is a combination of what we did in 4.1, right, finding antiderivatives just like you did on your gateways, and a little bit of like arithmetic. If you have your calculator, I'm going to show you some cool calculator tricks today too. I mean, not necessarily tricks, but some features anyway of your calculator. So if you will grab that out, we will see if we can get that to work with us. And we'll start an example. Okay, very basic antiderivative. Ignore the fact that it's got the limits at 2 and 5, and we're just going to do exactly what we did on the gateway on Wednesday and what you did back in section 4.1. What is the antiderivative of negative 3x? Yep, heard a couple different versions of it. Negative 3x squared over 2, or negative 3 over 2x squared. Okay, how about the antiderivative of the plus 4? Yeah, 4x. Okay, pretty good so far. All right, so that's nothing new. Now, what we aren't going to do is plus c. I'm going to do it on this one. Don't erase. I'm going to do it on this one so I can show you why we don't need it. But then after this question, we're not going to do it again because you'll see exactly why it's not necessary. So what we've done before is we put a plus c right here, correct? Okay, so humor me if you know why you don't need this, that's fine. But just humor me for the moment, I'll show you for everyone else too. And we're going to put a line at the back, and it's going to be the limits of integration 2 and 5 from the beginning. Good so far? Awesome. What we're going to do, according to this definition then, is we're going to take the number 5 from the top, and we're going to plug it in for x. So this is going to look like negative 3 times 5 squared over 2 plus 4 times 5 plus c. And all of this will be subtracting, and now we're going to plug in the 2. So we're going to have negative 3 times 2 squared over 2 plus 4 times 2 plus c. And what's going to happen to the c's? They're going to cancel because I've got a positive c right here, and then this negative distributed through will make this a negative c at the end. And that's the reason we don't need any c's when we do this, is because they always cancel out. Good? If you want to put them there, it's not going to hurt anything. They're absolutely unnecessary. The rest of this is arithmetic. You can put it into your calculator in multiple ways. I'd like to remind you and show you a few different cool things your calculator can do. One of them is actually a very cool new trick that you're going to see. But I want to just show you the evaluation thing as a reminder. I think we have seen this at different points before. I would like you to put the antiderivative in first. And I'm going to show you this version of it first. So we're going to put in the negative 3x squared over 2 plus 4x. Omitting the c because it's unnecessary. Okay, I'm supposed to be plugging 5 into this, right? Okay, there's 2 ways to do that directly, to just plug in 5. One of the ways to do that is just in your table. So if you go to your table, which is second graph, and put in the number 5, if your remote is set up correctly, mine's not, you change it. It spits back out at you negative 17.5. Did yours say that? Okay, good. That's great when the number is a nice, like terminating decimal and it's beautiful like that. But if it's got some ugly next to it, right, some sort of repeating decimal or something like that, and maybe ones that are not necessarily easy to see what the repeating comes from, this is not necessarily the best way to do it. So let me finish it with this one this way, and then we'll talk about another option. So this is negative 17.5. I have a minus in the middle, and now I can plug in the number 2 the same way. I get 2. So this is negative 19.5. Remind me if I forget, I want to talk about the negative part of this in a minute. But before I do that, I want to show you another way you can do this in your calculator. So back in your regular screen, your calculator, just the plain regular screen, you can hit vars, y vars, function, y1. And you should see a y1 now on your screen. It may have parentheses after it, depending on what operating system your calculator is using. If it doesn't, you're going to put a parenthesis, and you're going to put a 5 and close the parenthesis. So at this point now, my calculator screen says y1, 5, like this. And if I press enter, it will tell me that same negative 17.5. Why is it a little bit preferable to do it here? Well, if you had gotten an ugly value that you needed or wanted and felt like you should have in fractional form instead, you can do it from here very easily. How do you do that? You hit math, and it's the very first option underneath the math menu. It says frac. And if you press enter, it'll take the previous answer, it'll say A and S, you'll have the frac part after it, and if you press enter, it'll turn it back into a fraction, negative 35 over 2. Okay? So if I do this in fractional form, I would get negative 35 over 2. I'm going to get the same 2 over here, so I can do minus 2 if you wish, and then turn it back into a fraction as well. Or I can do it by hand, of course. It's negative 39 halves. Okay, we've seen some of those features in different ways before. Yes? Okay, but are you ready to see something I haven't shown you before? Because there are some really cool features here too. Okay, I'd like for you to go into your y equals and clear out the equation you put in. I'd like for us to put in the original equation we were given. Actually, this is a good place for me to talk about the negative part of it too before I do that. Put in negative 3x plus 4. And if you take a look at your window, just do a zoom 6 window. It's a standard window. You see that you have, and you should know this anyway from just some algebra courses you've had, this is a line with negative slope crossing at 4. It looks something like this. And I'm looking from 2 to 5. 2 is right here. 5 is over here. All of the area is underneath the curve. This is the area down here I'm finding. So it makes sense that my answer is negative. Okay, so if you're underneath the x-axis, your area is considered negative. If you're above the x-axis, the area is considered positive. I know that sort of defeats our perspective of area being a positive quantity, but for the purposes of what we're doing here, that's how we're measuring this quantity. Above the x-axis is positive, below the x-axis is negative. And it's very interesting because if it crosses the x-axis, right, some of it's above and some of it's below, we get something that we would kind of refer to as some sort of a net area. The area above is considered positive, the area below is considered negative, and it adds the positives and the negatives together, and it gives us some sort of a quantity that's representing the change between the two. So it's not exactly as clean cut as we might have a perspective of area as being. Okay, but this is why it's negative, and this is why it's appropriate. Okay. Now that you have this in your calculator, here's what I want you to do. Go back into your regular screen, your calculator, just plain old screen like this, like you had before. And I want you to choose Math 9. And depending on your version of your calculator, I think I might be at this point the only one who has an older version. Math 9 says F and INT. That part's correct no matter what. On my screen, it actually shows up in my screen now as F and INT with a parenthesis. That's probably not what yours shows up as. So I'm going to borrow Logan's and just peek over his shoulder for a moment and draw what his says. His shows like this. There's a little box down here. I'll do it in green like that. And a box up here. And there's some parentheses it throws in like this. And it has a D and it has another box. Okay, does yours look like that? Okay, most of your screens probably look like this at this point. All right, so let me use this one, and I'll go back up and show you what I do on mine. This right here mirrors exactly what you're trying to put in. You put it in just like it shows up. There's a 2 at the bottom. There's a 5 at the top. If you wish to type in the negative 3x plus 4 in the parentheses, you can. Or you can put the y1 in there since we put it in y1. So you can hit vars, y vars function y1. And the derivative is with respect to x, so you put an x at the end. My operating system doesn't look like that. I have to tell it that my equation is y1, my variable is x, my lower limit is 2, and my upper limit is 5. There's nothing wrong with it, it's just an older operating system. And if you press enter, it should give you negative 19.5, does it? Okay, good deal. So that's option number 2. The thing that happens if you do this is that you can get the exact answer, but I want to see that you know how to find the antiderivative along the way. So you're still going to find that antiderivative step, this one where I did right up here. And you're going to still show that you've evaluated and put those numbers in, the 5 and the 2. After that, it doesn't matter to me how you get to the negative 19.5. Are you going to enter it by hand? Are you going to scratch paper it? Are you going to use a calculator feature? It doesn't make any difference. Choose your favorite. Okay? But I've saved the most interesting one till last. Are you ready? Okay, we already put the graph in. Mine looks something like this. Does yours look something like this? Yes? Okay, good. What I want you to hit is I want you to hit the button that says Calc. It's above Trace. So the Trace button has a CALC menu above it. So if you hit second Calc or second Trace, option number 7 looks a lot like this Math 9 option. You've got that script S, you've got an f of x, you've got a dx. Do you see that? Choose option 7. On your screen, it says lower limit question mark. Did yours say that? Put 2, because that's our lower limit. Just type the number 2 and press enter. Then it says upper limit question mark. It's 5. Press 5, type 5 and press enter. What happened? It filled it in. I saw some grins even. You're like, oh, that was unexpected. It shaded it in. Did anybody's not shade it in? If so, I want to look at your calculator real quick to make sure we're okay. It shaded it in. Now, is it necessary to see it shaded in? No. And there are some caveats to doing that. Like, you have to make sure that your window actually has the 2 and the 5 in it. Like, if this window if it had told me that it wanted me to go from, like, I've set mine up right now to go negative 10 to 10. If my limits of integration had been like 15 to 20, my screen wouldn't show it and it wouldn't calculate it. I have to be within that window. But as long as I'm within that window, it shades it in. And the answer is on the bottom of the screen, negative 19.5. So that's sort of option number, I don't know what we're at this point, maybe about like 4 ways of finding the negative 19.5. Okay, all good? Okay, there are some limitations. This works really great when you have things that are like polynomials and stuff. It doesn't work so great with trig because we get like pi's and stuff involved, right? So this will give us an approximation that we can verify our trig work from, but it doesn't give us exact values. If there's radicals involved, it often will not give us nice values for radicals as well, right? Because square root of 3 doesn't come out as a perfect value. If you had square root of 9, you'd be fine. So there's some limitations to being able to use your calculator to do these, but it will give you an approximation regardless. Let's try the next one. It's trig, so now we're going to be back to doing it more by hand because of that. All right, so we have 1 plus sine x. You guys saw on your gateway some different things where you had sines squared and cosines being squared and tangents and secants and different things like that. Whenever you have squared trig functions, you're looking at trying to figure out how you can use some identities to change them. But this doesn't have that. The sine is not squared here, it's just sine. We know how to find the antiderivative of sine, so we don't have to use any trig identities. What is the antiderivative of the 1 at the beginning? X. And what's the antiderivative of sine? Minus cosine or negative cosine, right? We don't need a plus c here because we're evaluating it at 0 and pi, correct? So I'm going to draw my bar, and I'm going to put a pi, and I'm going to put a 0. You have to show that step, that you have found the antiderivative. You have to show the next step as well, that you're putting in the pi and the 0. So this is pi minus the cosine of pi, and then minus 0 minus the cosine of 0. Those are the required, if you will, steps. All right, now it's unit circle time, because I've got pi's and zeros. Those are definitely unit circle kind of values. So on the unit circle, 0 is right here. What is the cosine value when I'm on the right-hand side at that point? I'll do 0 first. It's 1. So this is where I am for the 1 right here. This is minus 1. I can put the 0 in if I wish, but we can leave it out. What about at pi? So at pi, I'm over here, right? This is pi. What's my cosine value when I'm at pi? Negative 1. So this is negative 1 like this, right? Minus a negative 1. There's a lot of negatives going on in this particular problem, so be careful not to lose track of where all the negatives are. This ends up being pi plus 1. This negative here, moving through, will actually make this another plus 1. So my value I actually get for my exact answer is pi plus 2. Okay? Now, pi is about 3.14, so this is approximately 5.14. We can check that with our calculator, and so let's just check that to make sure that it seems reasonable. Go ahead and put in the original equation, which is 1 plus sine x. And then let's practice using either Math 9 in your regular screen, or you can practice using the one that we just did where it shaded it in for you with the second trace button, number 7. And we want our second trace to go from 0 to pi. So your lower limit's 0, your upper limit's pi in either of those versions. Shade some nice things in, and it should tell you that we're at approximately 5.14. I'm not looking for you to answer 5.14. I want you to answer pi plus 2. But there's no reason your calculator can't verify that you found the right thing, right? Yeah, I mean, use your resources that you have to verify your correctness of your answers. Okay, is that all right? Okay. We have another fundamental theorem of calculus. And when we get to our next exam, this is one of those places where you're going to see me say, hey, you're going to memorize these. So the first one that we just saw over here, this was the fundamental theorem of calculus, right? Fundamental theorem of calculus right here. This one is called the second fundamental theorem of calculus. And it talks about the fact that if you take an antiderivative and then you take the derivative, those are inverse operations. That's what it says. If f is continuous on AB, and capital F of x is the antiderivative from a to x of f of t dt, then the derivative with respect to x of the antiderivative from a to x of f of t dt is f of x. Now, in a very simplistic question, what this is saying is, if you looked back at problem number 1 that we did, we had, what was our question again? Negative 3x plus 4. We found the antiderivative. It was negative 3x squared over 2 plus 4x. And if we were to find the derivative of that, it would take us right back to the original function we started with. It's a very simplistic question, and that's what this would be saying about it. Okay? Take an antiderivative, and then you take the derivative, and you're back where you started with. It's the way we teach, addition and subtraction, or multiplication and division. The problem is that not all of our functions are quite that easy, quite that simple, and quite that straightforward. So when they're not that simple, easy, or straightforward, what is this telling us? Well, it tells us that things are a little bit more complicated than just that. So we're going to do an example, number 3. And if you take a look at example number 3, what about it looks a little more complicated than what we just talked about? Yeah, that upper limit is not a number. And it's not even just a simple old x. It's a sine of x, right? Okay, so when we have a limit of integration that is a function itself, the process that this second fundamental theorem of calculus is talking about is a little bit more complicated. So I'd like to actually go through find the antiderivative and then find the derivative. So you can see that if you wanted to do it that way, you could do it, and how it would, sort of flesh out, how it would pan out for you. But then I'm going to actually show you what the fundamental theorem of calculus, the second one, says that we can do instead to shortcut the process. Okay? So if we were to actually find the antiderivative of this, we would say, okay, it's t squared over 2 plus 2t. And I'm supposed to be evaluating this at the sine of x and at 0. All good so far. Looks just like it does with the numbers. And then we would put the sine of x in for the x's, or t's in this case, sorry. So sine of x, so it would now be sine of x squared over 2 plus 2 sine x. And then we would substitute the 0 in, so we'd have 0 squared over 2 plus 2 times 0. This piece at the end is actually 0. That's what it works out to on this particular problem. That happens frequently, though not always. And we have the first piece. Okay, like this is the antiderivative. There's nothing about that that's different. The problem is that that's not what the question asked us to do. The question asked us to find the derivative of the antiderivative. So my second step would then be to find the derivative of this thing, okay? So this is still f of x at this point. And we're going to find f prime. So I need the derivative of this. Well, what do I have to do when I'm taking the derivative of sine squared in a problem? What's that? There's a multiplication rule or a chain rule, right? Either one. So you can either treat this as though it's sine x times sine x, or you can treat this as though there's an inside of sine x with an outside power of 2. I'm going to treat it like that. I'm going to treat it like it's a chain rule. So the chain rule says I take my 2 down to the front, and I decrease my power by 1. So this is now sine x to the power of 1. And I have to do the derivative of the sine x. And what's the derivative of the sine of x? Cosine of x. And this is all still divided by the 2 because coefficients come along for the ride. Right? Constant multipliers like this, when they're multiplied, come along for the ride. The other piece, a little easier. What's the derivative of 2 sine x? 2 cosine of x. I mean, clearly the 2's cancel, and that's, fine. But something about this feels like it's not quite right, because I now have sine x cosine x plus 2 cosine x. And when we started this whole problem, what we said was if we take the derivative and we take the antiderivative, it should be the same thing as we started with, and it is not. Right? This is not how this function started. It started as t plus 2. So why are there sines and cosines involved if it's t plus 2? Well, it's because that upper limit wasn't just x. The upper limit was a function of x, right? So what ends up happening? Well, I'd like to show you what ended up happening in a little bit different way. Notice that the sine cosine plus 2 cosine has cosine in both terms, right? I'm going to factor it out. So this is going to be sine x plus 2, and I'm going to put the cosine next to the back. So I'm just pulling the cosine of x out of this. Do you agree that these are the same thing? So what is this? Well, this piece right here is actually the t plus 2 with sine plugged in for t, right? This piece right here is f of sine of t. The other piece right here is the derivative of the sine of t. This is the f I'm going to do it this way. Sine of x's derivative. That's what cosine is, sine of x's derivative. So how can we use the fundamental principle or the second fundamental theorem of calculus instead of going through the derivative and the antiderivative each time? Because, this works. There's nothing wrong with what we just did. It finds the answer. But the second fundamental principle actually tells us that we can do it in a shortcut way. So let me show you what that shortcut way looks like. instead. So this is our first sort of thinking through option. What the second fundamental principle says I can do is I can simply take the t plus 2, right, that I'm given. So this is how I'm starting it. I'll just rewrite it again. 0 sine x dt. Is that I can take this sine of x and I can put it in for t. And then I can take the derivative of the sine of x at the end. And this will be the derivative of the function with respect to x. I don't have to go through any antiderivatives. I don't have to go through any, well, there's a tiny derivative I took. I took the derivative of the sine of x. But I don't have to take the derivative of the whole piece. I can evaluate at the upper limit, the function limit that's not a constant, right? I can evaluate at that, and then I can take the derivative of whatever that function is. That's very nice. That was really quick. The process we just went through before was pretty complicated, or at least lengthy. So let's take a look at another one. What do you notice about this one that's a little different, though? Because there is a caveat to this one that's different. There's two variables. The first one that I did had just a constant on the bottom. And in fact, the fundamental principle says I need a constant on the bottom. It only really works if I have a constant on the bottom. So what do I have to do? Well, I actually have to apply a property, of integrals that we encountered before. Do you remember we had a principle that says that if we go from the integral from a to b, and there's a c in between them, like this, that we could break it apart and we could go from a to c, and then we could go from c to b? Do you remember doing that? We said we can break it in a couple pieces. That's what we're going to do. We're going to break it into a couple pieces. And the interesting thing is that it doesn't matter where we break it, so we might as well break it at 0. But you can pick a number. It won't change anything. And the reason it won't change anything is because the fundamental principle says it can be any a value at the bottom. I don't have to have 0. But I'm going to pick something, so I'm just going to pick 0. So over here, what we're going to do is we're going to break this apart. Instead of it going from x to 3 minus x, I'm going to go from x to 0 of the same function, t squared plus 4 dt. And then I'm going to go from 0 to 3 minus x of t squared plus 4 dt. I'll move the other stuff over. Okay, the second one is in the form of the fundamental principle. It's got the constant at the bottom, variable at the top. Agreed? What about the first one? It's flipped, right? Yeah. So this is the other property that happened the same time that we encountered this property. It says if I flip my limits of integration, I just make the I make the integral negative. So I'm going to flip my limits of integration here and make it negative. So this will be a negative, the integral from 0 to x now, of the t squared plus 4 dt. And then I have the integral from 0 to 3 minus x, and I have t squared plus 4 dt. Okay, pretty good so far. So I don't really want to take any integrals, and I don't want to do any derivatives, right? I want to use the fundamental principle so I don't have to do any of those things. This is f of x so far. All I've done is just rewrite it in some different ways. I want to find the derivative. And the fundamental principle says, especially on the first one, that I can just take the negatives in front of it. I can just take the x and I can put it in and be done. So this is really just x squared plus 4. Easy peasy on the first one because the upper limit's just x. The other one, though, the upper limit's not just x. So while I do, in fact, put the 3 minus t in for, 3 minus x, in for t, like this, I do have a function that's not just x. So I need to take the derivative of 3 minus x. What is the derivative of 3 minus x? It's not hard. It's negative 1. Last time the derivative sign was cosine, so it's the derivative of whatever that upper limit is. You could also think of it in much the same way, and like, why do I not have to worry about x? Well, what's the derivative of x? 1. So do I really need to write times 1 at the end here? No. If you want to remind yourself to do that step every time, feel free to do so. And then we're just going to multiply, clean this all up. Okay, multiply it all out. So I have negative x squared minus 4. I'll put my negative at the beginning here, just move my negative over here. Then I have 9 minus 6x plus x squared plus 4. And we'll distribute a negative. So this is negative x squared minus 4 minus, oh wait, look, I have 9 and 4, that's 15. So minus 15 plus 6x minus x squared. That's two negative x squareds. I have a positive 6x, and then I have, looks like negative 19. It should have been 13. I was like, I'm off by 2. This was a 13. My apologies. Moving too fast. That's a 17 at the end. Okay, I think I fixed it all. That's the second fundamental principle of calculus, or theorem of calculus. Okay, ready for the next one? All right, what we're doing now is we're actually taking a look at some curves, and we're trying to figure out how we can use these principles of calculus, these fundamental theorems, to find given area descriptions. So this one says we've got the area of a region and it's bounded by some curves. So the first thing I need to do is I need to draw the picture of what's going on, or I'm not going to be able to figure out, at least not very easily, what areas I'm looking for in terms of antiderivatives and so forth. So my graph says I should have an x squared. So this is the graph of x squared. And a sketch is usually sufficient. I'm not looking for something super, detailed. It's usually enough. And I've got the line x equal to 2. What's the line x equal to look like? Not horizontal? Vertical. So it's a vertical line over here at 2. So it looks something like this. So at this point right here, I could actually, this is the curve y equal x squared. So I actually am at a height of 4. If you have some, some perspective of it right here. And it says it's supposed to be bounded by these two curves. So this curve right here, this curve right here, and the x-axis, which is this one. So it's a sketch, but do you see where the trapped area is supposed to be if it's drawn well? You should. The trapped area is right here. This is what I'm supposed to be finding the area of. So I'm going to find an integral. What's the lowest x value of this shaded area? Where does it start? 0. What is the upper end of the x values area? 2. So keep in mind we're looking at the x values on this. What function is bounding it from above? What function do I shade underneath? X squared. So this is the x squared function. And my derivative is with respect to x. Okay? So what's the antiderivative of x squared?
1/3 x.
Okay, 1/3 x cubed, or x cubed over 3. We're going to evaluate at 2 and at 0. So this is 1/3 2 cubed minus 1/3 0 cubed. This piece, of course, is 0. What is 2 cubed? 8. So this is 8/3. I don't think it's worth your time to grab a calculator. Not for this one. It's okay? All right. One more thing in this section. It's called the average value for integrals. The average value for integrals says the following. If f is integrable on ab, then the average value of the function on the interval ab is 1 over b minus a, integral from a to b, of f of x dx. What's the only piece of this that's sort of new that we haven't done? Yeah, the beginning part. This piece at the beginning. So what is this piece at the beginning doing? So when you average things, you're trying to balance something over whatever domain you're looking at. Right? When we give you your class average, right? If I want to know the average grade of everyone in this class, I'd take all your grades and I'd add them together and I'd divide by the number of students, right? If you wanted to find your individual grade in this class, you take all your grades or all of your points, you add them together and divide by the number of points that are available to you, right? That's what's going on here. We're dividing by or multiplying by the reciprocal of the length of the interval. And it's actually very interesting what happens from a graphical standpoint. So we will look at that when we get to our example of what this is really doing for us from the standpoint of the graph. Okay? So our example is a really straightforward one. It's just the square root of x, but we haven't done a square root today, so I thought that we'd throw one in there at the end, show you what happens when we've got radicals involved. So we're trying to find the average value over the given interval. The definition we just saw up before says that I'm going to do 1 over. It's going to be 9 minus 4 at the beginning. My integral is going to go from 4 to 9. And square root of x, written in a more helpful way, would be x to the 1/2. So that's how I'll write it. Is the setup okay? The calculation for these is not all that much different. I mean, you just have this different, piece at the beginning. There's really not a lot of calculation difference. Let's find the antiderivatives. This is 1/5 at the beginning. What's the antiderivative of x to the 1/2? Okay, you're right. So this is x to the 3/2, and then we're going to divide by 3/2. Or if you prefer, you can write it as multiplication by 2/3. And all of this has our limits of integration 9 and 4 at the end of it. Nine and 4 are pretty nice values because square roots of 9 and square roots of 4 work out really well. So if you wanted to enter this directly into there, you could. Like in your calculator, it's going to give you some nice values. At the beginning, I have 2/15. If instead you would rather actually rewrite this is the square root of x cubed, 9 and 4. You can do that. Somewhere along the way, I want to see that you've put the 9 and the 4 in. So this is the square root of 9 cubed minus 2/15, and I've got the square root of 4 cubed. Somewhere along the way, some version of it being plugged in. It doesn't have to be in the radical form. It could be in the fractional exponent form too. That would be fine. All right, so computations, you can do this lots of ways. I'm not terribly concerned that you can't do the computation. I do want to make sure that you're careful. This will not give you a nice decimal value if you try to do it in table. So putting it back into fractional form is going to be valuable. It is 38/15 as a fraction. If you think about the square root of 9 cubed, it's really the square root of 9, which is 3, and then cubed, so it's 27. So you're getting a 27 at the beginning here. So 2/15 times 27. And then this one would be 2/15 times, what do we have? 2 cubed, 8, right? So this would be at 8. So it ends up being 38/15. Okay, is that okay in terms of the calculation piece of it? Okay. I want to show you what happens in your calculator in terms of what this is really doing, though. Because I can throw out all kinds of let's just decide we're going to do this to it, and it have no physical meaning to anything going on. But there is a meaning behind what's happening here. So take your calculator, go ahead and put in the original equation square root of x, okay? And I'd like for your window to go from 0 to 9. So make your window go from 0 to 9 on x. For your y minimum, 0 as well is fine. Your max can be probably about 5 or so, and it'll be okay. And you'll end up with a graph that looks like, I'll sketch my graph over here in case you don't have a screen to see for yourself today. The graph looks something like this. Okay, so look right? That should make sense. You know the graph square root of x. Our interval really only goes from 4 to 9. So if I were to do the math 7 here, which I'm going to ask that you do, so go ahead and do second trace, calc 7, I mean, and do your lower limit of 4 and your upper limit of 9, it's going to shade it in. And it's going to look now like this. Okay, everybody good? Okay, I haven't done anything with averaging yet. I'd like for you to go back into y equals, and in y2, I'd like you to put the answer we got. It's 38 over 15. So just type into y2 38 over 15. And I'd like for you to see that it's going to cut through the graph. That's not very good. Let's see about right there. It's going to look something like that. Here's what the average value does. It takes this non-rectangular region. It's got a curve at the top of it. It's all shaded in green, right? And it tells you that if you had found the area of the rectangular region that has the height, in this case 38 over 5, it would be the same area as the green region we originally have. Okay, so imagine, this is like taking Play-Doh in a certain shape and remolding it. You didn't change the volume, or in this case we would be looking at area, right? You didn't change the area, you just changed its shape. Yeah? That's what averaging does. It takes an arbitrary region and it makes it into a rectangular region of a specific height. The specific height here is the 38 over 15 that we just found. It's interesting, right? It allows us to find the average of something in a contextual sense. All right, so bit of reminder, what's coming up? I'm going to keep my screen, my volume going. So we are done with 4.4. We are going to move Wednesday's quiz, the homework that's due today, and we're going to move our 4.5 all into Monday. And we won't need to meet on Wednesday. Are you sad? You're not sad? Oh, I'm so sorry you're not sad. All right, so I will change it inside of Canvas. Quiz on Monday. Homework 4.4 is due on Monday. All right, and we will do 4.5 in class on Monday. Lovely. You will still be able to take your gateway clear until Wednesday, though. That's not going to change, okay, if you need those days.